whereas they might not necessarily be funding sources, they definitely could be collaborators that could help reduce overhead rates and others, and allow us to, you know, fund you grad students and others, and fund more of them than we would have been able to otherwise. So that is sort of what I was looking at for research coming here and in the future. This very long phrase of urban adaptation for climate change and extreme weather events in the electric power sector, right? There's a lot of different really fun, really interesting stuff that we can do, both theoretically as well as applied. And I should also mention that, you know, I advise the city of Pittsburgh, I sit on some St. Paul, Minnesota groups, and I hear that here, you are very, very lucky to have the mayor as part of your faculty. So that is really exciting to me, because I know that a lot of the stuff that we all do in the classroom can actually get used in the real world. Now, speaking about classroom, I'd like to switch over to the type of teaching, and I have about 10 minutes left, I believe. So 10 minutes on teaching, I'm right on target. So I have 4 different areas in which I do teaching. I define this a little broadly. You have, of course, the very classical classroom setting. I'm really excited to see that these tables are not like those here. I've also turned like the big auditorium rooms, pluses and minuses for teaching in them. But in addition to just classroom teaching, which is really important and you can get a lot out of it, there are other forms of teaching that are very important to me. One of these is mentoring students. The image on the upper right is my 2 students, Catherine Bradford and Miriam Heglin. Catherine, they're both undergrads. They had done that, remember that census block, you know, gray Pittsburgh thingy with the X's and stuff. They had done that research with me. It started in a class that they took with me. They worked on it over the summer, and then after they were done, we sent them to a conference courtesy of Civil Environmental Engineering in Los Angeles. From Pittsburgh, that's kind of a far trip, excuse me, so, you know, really thank the Civil Environmental Engineering Department at CMU for funding that. And then after they were done that, they had the poster presentation, they had a peer-reviewed publication accepted in ES&T. You know, I was a co-author on this, which is a pretty good impact factor. It's one of the ratings for, you know, how you decide if the journal's good or not. And then they won a undergrad-wide presentation award at CMU for their poster. So that's another type of teaching, mentoring students, working with them to help them succeed. And if that means I'm like 2nd or 3rd author on a publication, then that's what we'll do. Down here on the bottom left, there's also a lot of outreach to practitioners. I'm not sure how many of you all ended up getting my CV or whatever, but I do a lot of work with practitioners as well. There's a little bit of consulting I do. I mentioned that I work at the city of Pittsburgh. I'm on their advisory board for different resiliency pieces. I do the same for St. Paul. I used to do some when I was in DC as a consultant there as well. And you have some of these workshops, like here we're walking the city through what are their shocks and stresses to their critical infrastructure in town that they need to worry about now and in the future. And so it's helping them sort of walk through how to do that preparation. In addition, I also, as was mentioned earlier, I work at the American Geophysical Union as their board of directors. And they have something called the Thriving Earth Exchange, which seeks to connect cities with different scientists in order to help the good engineering work that we do get used in the real world. And so that is part of the 100RC, which is a big Rockefeller thing. It's really kind of important in the resilience world, but it sounds like I'm not getting any shaking heads, so you probably haven't heard of it. It's fine. And then the last one, of course, on the bottom right, is K through 12 outreach. When I was a PhD student at Carnegie Mellon University, I was a little bored. I had nothing to do. You know, writing dissertations, that takes no time, right? You guys are probably all out partying every evening. So in addition to that, I decided that I wanted to start, yeah, I got some smiles in the back. I decided to start a K through 12 outreach program. So we took 10th grade students from the local community for 1 week at Carnegie Mellon University in the Succeed Summer Program, which is the Summer Center for Climate, Energy, and Environmental Decision Making. So we brought them in, we taught them engineering concepts, we took them to the local coal power plant, took them to the local nuclear power plant, a battery factory, a whole bunch of different things where they could go in person and see a lot of these things. We also had an outreach perspective in this, which might not be apparent from that image, but we did have underrepresented minorities that attended. And we actually ended up realizing at some point that they had no plans to go to college because they had no idea that it could be free for some students. And so we had to take them aside and, hey guys, you really can apply. This, you know, the state's got a lot of money for you. So a lot of those outreach efforts as well. As part of that, we also did a 2-day teacher workshop developing curriculum meeting next generation science standards and common core curriculum, which is the science standards and the math standards that all teachers have to teach to in Pennsylvania. And so these are sort of the 4 facets of the teaching that I like to do. And I was asked to suggest some potential classes that I could teach here. So here's the first one. How many of you guys have seen this diagram before? Yeah, yes, all right, great. So this is one of the standard Sankey diagrams, or energy flow diagrams, showing, and this is by Lawrence Livermore National Labs, showing where all the energy goes. We get the sources on this side, so it's like solar, nuclear, gas, whatever. It goes some things along the way, and it gets used in different ways, and all at the end is what happens. And you see that roughly, and there's about 100 terawatts, I believe, 100 quads of energy used in 2013 in the US. And so roughly 38% actually gets used, and the other 59% is waste energy. So because of this, the National Academy of Sciences has started their Science and Engineering program, ambassadorship program, in Pittsburgh, Pennsylvania, focused on energy. As part of this, we are creating a class, this would be the 2nd year that it's run, on Energy 101. So it's basically trying to understand these sources, the transmission, distribution, and end use, and all the different parts that go in this. It's taught at an undergrad level, and it's currently co-taught between 2 universities, CMU and University of Pittsburgh in Pittsburgh, Pennsylvania. They would like to take this and replicate it in other universities. And so basically, while it's being taught at CMU and University of Pittsburgh, also teach it, say, here. So that was one class that I considered teaching. I recognize that according to the syllabus I had, that it might be an overlap with these other 2 classes. I have no idea about that because I haven't actually chatted with the folks who run those 2 classes. But now this is sort of like what we want our undergrads when they graduate and go out to consulting or to industry. We want them to be able to get some very basic concepts about this diagram so they know about source, transmission, distribution, and use, and any sort of recycling. So that's one of the classes. The second class, more at a master's level class, is a class that I've now taught twice at Carnegie Mellon University. And I actually changed the title here slightly from the class I taught at CMU. But the class is looking at international critical infrastructure in developing and developed countries, specifically in river deltas or rivers, and trying to understand, because of climate change and population changes, things are going to change in the future. So how do you, as a good engineer, whether that be structural, mechanical, chemical, materials, any of these types, if you're going to be a good engineer and go out and do work in these areas to prepare for whatever time frame your clients have, what should you be able to do? And so a lot of the class focuses both on different things that happen in the river deltas. You know, the Mekong River Delta and the Yangtze have different characteristics than the Mississippi, and different economics in the area that drive them, so you want to protect different things. There's also a lot of interest in the hydroelectric power and how this will play out in the future. You know, you have the 3 gorgeous dams, the biggest dam in the world. You have a lot in Brazil as well. There's a couple very, very large 8 gigawatt plants. Those are basically 16 times bigger than most coal power plants, so really big. And then you have you know, some interesting political things that are happening. For instance, in the Nile River is the Aswan High Dam, and just upstream, Ethiopia is planning to put in their own dam, which will affect what will happen at the Aswan High Dam. And there's a whole bunch of contentious political stuff that's happening there that's super fun to study, but also we get to do sedimentation and fluid flow and mechanics and when dam failures occur and stuff like that. But one of the things that comes out of this is that the students come out writing a consulting proposal to a group like the World Bank for a particular type of adaptation. They have to go very much in depth, use some engineering economics, use some statics, mechanics, and other flows. One of the ones that I had last year that was pretty good was looking at a hydroelectric power plant, and looking at how reservoir changes would affect the flow through the penstock down to the turbine, where when it hits the turbine, there's some generation, there's a drop in the waters, kinetic energy, potential energy. You guys have done a lot of that, I'm sure, in your classes. And then the power going out, as well as some interest going out through the river. And so the question that this particular student has was, given reservoir changes, in this case the reservoir was increasing, what is going on with the structure itself? How will it change? It was more of a civil engineering perhaps than mechanical engineering, but then some of the mechanical engineering pieces that may or may not have to change in the dam itself to support that. So I thought that was interesting. We'd like to teach something like that again. And then the third class, a PhD level class, I took a look at the mechanical engineering course offerings. And what I thought was that in today's society, there's a lot of really great stuff you can do working in your own little box and going and just doing the mechanical engineering that your boss tells you to. And that's great and really useful. And you need those deep dives, you need those people to be able to do that. But you also need people who understand a little bit about climate and extreme weather, these things that are really going to be affecting us in the future, and can take meteorological data, NetCDF files, and GIS and other pieces, and feed them in to different pieces so they can prevent failures like this one from an ice storm from happening. And so that, this one is a newer class. I haven't taught anything like it before, so I would want to think about it a little bit more, but I think those are some of the concepts that I would want a PhD student who is a little higher level thinking to be able to come out with and be able to synthesize some of these outside pieces as well as do the deep dives in their particular discipline. And so this is my email address as well as some of the papers that were referenced in the talk, and I'm exactly at 45 minutes, so back over to you guys.
So we've got time for questions.
Yeah, thank you for the talk. Can you go back to one of your other slides with the cost versus, I guess, emissions reduction?
Yeah.
Probably slide 2.
Oh, that one. Yeah.
Yeah, that's right. What are the bigger blocks? Do you know offhand what those are? Like the really big ones that have huge emissions?
These ones that have a lot of emissions pieces?
Yeah. What are those?
Yeah. So this one was a light bulb switch. These ones were changing your refrigerator over. This one was also an energy efficiency savings regarding putting a certain type of EPA star appliances. So there's a lot in that. And I think, if I remember correctly, this one was insulation in your house. So moving from like R10 to R30 or something like that.
So kind of low cost but really big effects.
Yeah, pretty much. And there are things that, in a lot of ways, since the government subsidizes a lot of these two things at the moment, like especially if you're poor, so the environmental justice piece coming in, you can actually get the federal government to pay you, or you used to be able to, I don't know if it's still true, but pay for a new refrigerator. So it was like really super cheap to put it in.
So on this, in this subject, so tell me about the decision support tool aspect of it. So I feel like, I think people, I've seen those graphs or something before, right? But it sounds like the interesting part is what to do with it, right? I mean, how do you change people's minds, or how do you influence people on the basis of that information?
So, when I've been showing this around, for the most part, what I see is decision makers saying, okay, well, these 18 things, they're below the line, we're going to do them. And I'm like, well, don't you care about other things, like air quality, or increases in property value, or whatever it is? And they're like, yes, we do. And I'm like, all right, so how do you want to trade these off? We don't know yet. So that's really where this decision support tool comes in. I like having things being open, because then anyone can go in and use the information in there. Of course, we're having a push towards more open stuff. But part of the interest in this is understanding we're allowing decision makers to put in what we call their own utility function. So how much they care about certain different aspects or characteristics. For instance, if you were buying a car, you might care more about the brand than you do about the color. versus whether it's 2 doors or 4 doors. I don't know, but maybe you're a different preference on this. So when decision makers have those abilities to even just rank order things, like I care most about this and then a little bit less about this and a little bit less about this, they might be able to compare some of these things more appropriately. The second piece is that with a researcher at Leeds University in England, who is very, very good at charts and numeracy, like that's her big thing, we're working to take this and make it intelligible to someone who is not all of us sitting in this room. Like for the most part, you guys all know how to read XY graphs, kind of get a feeling what this means. But if I give this to my mom, her eyes would glaze over and she wouldn't understand how to get it. So that's part as well of this open decision support tool, is figuring out those next steps to make this more accessible to decision makers who need to look at it, get something quickly out of it, and to some extent might not be able to read XY graphs. A very good example of doing this is when we used to tell people they had certain flood risks on their house, and nobody got it, and then NOAA made their surging, and NOAA and Climate Central both made sea level rise toolkits. We could go in and then you could put in a certain sea level rise and see, oh, this is what this means. All these things around me are flooded, but my house is okay, or whatever the scenario was. And we see that sort of ability to talk about this information as being more useful. That's not my area of expertise, of course. I would have other folks work on me with that. I haven't actually looked to see if there's folks that work on numeracy here. Maybe there are. But that is some of the pieces moving forward on that. Yeah.
During your postdoc, who's been really your biggest funding source or supporter? Do you think that'll continue, or you'll shift to another agency possibly?
Yeah, so my postdoc was 2011, then I went off to DC and was consulting. So as a research scientist, is that what you mean? The last 3 years?
Mm-hmm.
My biggest funder has been the DOE on the solar photovoltaic work. They fund quite a bit of money to do this, and they are continuing some funding in the future. It's a big enterprise called Sirius, which I know it stands for something, and I'm a really bad person because they give me a lot of money and I should know what it stands for, but it's basically solar energy in both India and the United States, and how we can both do technology transfer and it runs the gamut from improved materials and improved mechanics and some of the silicon wafers that I was chatting with some folks about earlier today, moving all the way to some more open decision support tools that I don't work on, but others in the project are. And that's about a $58 million project overall. So that's the biggest one. The second biggest one is the NOAA SARP NSF RIPS proposal, which at this point with both funding streams is a little over $2.5 million. I saw the grad student in the back.
I was curious how you get connected with communities and cities to advise them on the urban development. Do they pursue you? Do you pursue them? Or is it a bit of both?
Yeah, so in my experience, no city or community has pursued me yet. Hopefully in the future that will happen. But at the moment, cities and communities are so overwhelmed with day-to-day running of their own communities that, they work more than all of us do. I'm sorry to say that. I know we should, probably work more, but when I chat with some of the mayor's staff, they're up at 6 a.m. and they're still working at midnight, and it's insane. So they just don't have the time or energy to do these things. So first you establish some sort of credibility. And for me, that would be research scientists at Carnegie Mellon, done a bunch of this in other cities or communities. But for you guys who may not have, I'm a grad student at CSU, and whatever I do is free for you. And so then cities and communities are like, free. All right, well I have all these projects, and you have to sort of work your way up, and it does take trust over time to build that up. But I think you guys got a really good in with your mayor and the faculty, like that. I'm sure whatever methods that you've created to sort of foster those collaborations are probably one of your best methods forward. It has been easier for me with the smaller communities. I used to work with about 10 different communities on a FEMA project. That was really simple because you could get to the person you need right away. Some of these bigger cities take a little bit longer and you have to work your way up. But as long as a student you emphasize, I'm free for you, It will never cost you money, and I will be unbiased because I'm not, trying to sell you anything. Usually folks are quite happy to work with you.
I was going back to the question before that, and you were talking about your two funded projects right now, and the first big DOE one. Because clearly to do this kind of work is very interdisciplinary and very collaborative. So help me understand your role and your students' role in this gigantic project.
So in the DOE one, I do not have any students working with me. It's
Okay,
funding my
it's
time.
you, yeah.
It's funding my time. So what I've done is created a server that goes and obtains the generation data roughly every minute. And it's protected, hard protected in a couple different ways, so it won't go out. And so it pulls the data from 50 different power plants roughly every minute. And then what I do is I created some code to go through and clean the data, because data are very dirty and you have to reduce some of it in order to be able to do stuff. And then I went through and did some of the frequency domain analysis, including a special type of function that works on non-uniform time steps called the lone periodogram, and calculated this through. At this point, my mentor, who's my collaborator, who I would look for more folks like him in the future, basically had brought the money in, funded me on it, and has sort of stepped back and said go. So he is the second author on the paper and helped advise me along the way. But a lot of this is my piece. And whatever I choose to do with the money moving forward will be my work. At the moment, the way our contract is written, we're not supposed to fund students, and I still haven't figured out why exactly. But I'm working on that piece. Yeah.
Since you're showing us this slide, I'm actually curious about some of the details. So like, if I look at you made the argument, I think, that the kind of high frequency tail improves, right, with more plants. So it seems this data sort of inherently has some noise in it. So how do I kind of understand that the benefit exceeds the noise? And then the second question is, how much benefit on this kind of a scale do I need to really have it translate to something practical?
So I'm going to go to the talk I just gave at the American Meteorological Society that has the perfect graph for you on this.
Great.
So this is it. So what we did here, or what I did, was then take all the 50 power plants that had good data in them and combine them in all combinatorics possible. So then you could average across and obtain values. And so what we have here is the number of photovoltaic sites that were averaged together. So if there was only one averaged together, that meant you had 50 points, 50 data points there. If you had 5 averaged together, you can do 50, choose 5, and however many that is the number that were averaged together. On the y-axis is the fraction of the power spectral density of one plant. So for each of these curves, we fit a line, or I fit a line, including uncertainty on them. So on those, where'd my pointer thing go? So we fit a line here, including uncertainty in this log-log diagram, and then with all the combinatorics averaged over them, so this is an average value. But then it's seeing if you split through this at something that is 10 minutes, or an hour, or over here at 6 hours. So making those horizontal slices, taking all of the points that were here then and over there, and seeing what fraction this, if it was averaging 20 plants, this purple was of gray, of black, to get this value. So perhaps a better way to say this is averaging over all possible combinations. As you increase the number of PV sites, for 6 hours you do see a reduction in the variability. And that's what our power spectral density is. It's a representation of variability. As you continue to go to finer and finer temporal resolution, you start to have even finer and finer, or more and more reduction in variability. But you do not get to the square root of n limitation that one would expect on solar power. Actually, this is the solar power graph, and this is wind power. You see a lot more variability reduced through wind power with a similar number of plants. This is 20 and this is 20, which has some interesting policy implications for other folks, but I'm not working on that. Yeah.
So, in a model like this, what do you assume in terms of like geographical spacing between the plants? Is that based on real data, or?
Based on real data, I have all the lat longs of all the power plants, including some of their solar modules, all the inverters, stuff like that.
Mhm.
So I know exactly where they are. I did start with adding the plants together by, on some of the graphs, one of the ones I showed you, of adding the closest plants together first, with the idea in mind being that plants that are closer are more likely to have the same cloud passing over them at similar times. So you should see some autocorrelation in the signal, right? But then that second graph that I showed, that was the average of all the combinatorics, it would take plants A, and then for its second plants, any one of the other 49 plants added together. So it sort of smooths out some of the geographic variability that one would expect to obtain.
So it is kind of, is there sort of a correlation length then, that, you know, if you're within 100 miles, you're sort of correlated, and that relates to the clouds?
Yeah, so it's a function of the time period and the climatology of the area, right? So if you're looking at variability at a 1 minute or 5 minute spectrum, the variability is not actually entirely correlated much between plants. You can have things that are like as little as 7 miles apart. Lots of peer reviewed literature has shown this. And the correlation will actually be pretty low because the clouds are just spiking oddly. The correlation will be high because they're close enough. But the ones that are farther apart, like as you're starting to get up to 10, 20 miles even, you're seeing at that point, that is when there's almost no correlation. The studies that have shown that have all been over places like Germany, where they have multiple data sets, which has highly variable clouds and weather. Gujarat, India is a much drier, less cloud-prone climate. Part of the next things that I'm trying to do for this is with the weather station data, see if I can see individual clouds passing overhead. And you can sort of track, there'll be like one cloud and one spike, and that's all that happens. And with what I know of the prevailing winds in the areas, you can sort of see some of that occur. So it is a function of both the time resolution you're looking at. I guess I didn't say much about that, but the fact that if you're looking at an hour average data and taking the smoothing over 1 hour, that's of course going to be different than your like 5 minute intervals. But you can do much of the theory, like the square root of n comes from the theoretical speed that clouds pass overhead and how long they'll take to go between certain plants at certain sizes.
How extensible do you think your kind of skills that you've gotten over the years would be to other problems? Obviously, we've got some different constituencies here in Colorado than say in the Northeast, so things like fire and flood and those types of things.
Yeah, so I'm a certified floodplain manager, so I am really good at flood stuff. A certified floodplain manager is a certificate you get from the Association of State Floodplain Managers that is recognized by the National Flood Insurance Program, so I can make insurance decisions on your house. I know less about wildfires. I actually wanted to teach my class this year that was the River Deltas one on wildfires, but then my department had moved it to right now, and I couldn't do both interviews and teach a brand new class at the same time. So I'm going to have to hold on that a little bit. But there is a National Academy of Sciences report that will be coming out soon on extreme weather and climate change attribution that has some things to say about wildfires, which I'm not allowed to say too much about other than it has some things to say about wildfires. But if anybody here is doing proposals in that space, they will find that likely a very, very useful citation. So it's a little after 4. I'm happy to entertain more questions. I know I put my one grad student to sleep back there, so that's good.
Only one.
Come on, I guess I better know.
So let's
All right.
thank Kelly again.